In a letter to his son, Albert Einstein wrote, "Life is like riding a bicycle. To keep your balance, you must keep moving." And move he did, balance he kept, especially in the year 1905, called the Miracle Year, a year where Albert Einstein himself described as a year where a storm broke loose in his mind. Within a 6-month period, this 26-year-old Einstein submitted 4 papers that revolutionized science forever. Photoelectric effect, Brownian motion, special relativity, E equals mc squared. Each of these papers started multiple new fields of science altogether, which are still studied intensely today. Professional researchers from all over the world, including myself, dedicate their entire career studying a subfield of a subfield created by just one of these papers from 1905. Science has not seen a year like this since 1666. 23-year-old Isaac Newton was holed up in his mother's home during the Great Plague that shut down Cambridge University. What did you do when you were holed up in your mother's home during the recent coronavirus shutdown? While Newton was social distancing from the Royal Society, he split light into colors. Meanwhile, we were splitting sourdough into pans. Newton invented calculus to take slopes of the curve. Meanwhile, we were trying to flatten the curve, during which Newton invented the laws of motion and gravity. 26 and 23 years old. The energy properties of light, the light quanta. You've got to be kidding me. Young 20-year-olds making gargantuous leaps in science and humanity. Meanwhile, 20-year-olds today in modern times, just 10 years before the Miracle Year, a prominent physicist, Albert Michelson, said, "Fundamental laws and facts of physical science have all been discovered, and these are now so firmly established that the possibility of their ever being supplanted in consequence of new discoveries is exceedingly remote." In modern day English, ain't nothing new to be discovered in physics anymore. He was wrong. By the way, Michelson was not just some ordinary physicist. He was a brilliant one that played a key role in the establishment of relativity theory. Furthermore, he was the first American to win the Nobel in 1907 for measuring the speed of light. That's got to be the strongest pickup line ever. Hi, nice to meet you. Oh, beautiful weather today. Oh, me? I'm an astronaut. Hi, nice to meet you. Oh, beautiful place, nice food, good weather. Oh, me? I was the person who measured the speed of light. This 26-year-old was examining patents in Bern, Switzerland as his full-time job because he couldn't land an academic job. Despite working 8 hours a day, 6 days a week, he had time to, revolutionize science 4 times over within a 6-month period. I just want you to pause on this for a moment. We all hear Einstein's amazing and a genius and great, but I want to make this concrete. Pause on this. If any of my PhD students at Stanford published 4 papers in a single year of any moderate quality in a peer-reviewed journal, I would grant them a PhD on the spot. It rarely ever happens because writing a quality paper takes a freaking long time. And by the way, not just any old 4 papers. This paper was a key ingredient that initiated the field of quantum mechanics. This paper proved the existence of atoms. These 2 papers gave us the equations and showed how to apply them to the universe. It's fair to say that Einstein created the field of cosmology as the physics of the whole universe. Think about this. From the smallest metric, the quanta, to the largest entity, the cosmos, in a 6-month period. A storm broke loose in my mind. Yeah, no joke. A cosmic storm broke loose in Einstein's brain in 1905. The remarkable thing about Einstein is that 2 very disparate and distinct concepts can simultaneously exist at the same time in Einstein's brain. It's like the opposite of the uncertainty principle. 2 ideas can co-localize at the same time, same place, with absolute certainty inside of this person's brain. After submitting these papers, Einstein was so exhausted that he went to bed and didn't do anything for 2 weeks. How many Nobel Prizes did Albert Einstein win in his career? When I ask this question to my graduate students, I get all sorts of different answers. 7, 3, 10. It turns out he only won a single Nobel Prize. Only, right. Oh, I only won a single Nobel Prize. No. It's a phenomenal, remarkable thing just to win any. But to a scientist like Einstein, who's had so much influence in our physical universe, in the world of science, one just seems like a surprisingly small number. And the one he got it for was for the photoelectric effect, which he totally deserves. But in my mind, he should have gotten all 4 of these just in the year 1905. Certainly, when special relativity became general relativity about a decade later, absolutely he should have got it for that one. To the general non-scientist, Einstein's theories on relativity and E=mc² are the most famous in popular culture. But in my opinion, and an opinion shared by many other scientists, his discoveries on Brownian motion are the most impactful to our everyday lives. In this work, he proved the physical existence of atoms and molecules as something you can touch and feel and count and measure. Not a lot of people know this, including the graduate students that I teach, but Einstein was doing fluid mechanics, which happens to be my career specialty. Einstein's PhD thesis was all about the viscosity of fluid suspensions. Interestingly, his most cited paper out of these 4 papers is his papers on Brownian motion and fluid mechanics. This might be surprising to you, but in the early 1900s, only 120 years ago, not everyone believed that atoms really existed, meaning atoms were actually things that you can touch and feel and count and observe and measure. People believed that the concept of the atom was a mathematical convenience, a metaphysical speculation, but one that didn't really exist in reality. Lots of really smart people were atom non-believers. Ernst Mach, of the Mach number from aerodynamics, airplanes traveling 1 Mach, 2 Mach, that Mach, rejected the atom hypothesis and said science should only deal with directly observable phenomena. Wilhelm Ostwald, who won the Nobel Prize in Chemistry in 1909, considered one of the founding fathers of the field of physical chemistry and a giant in catalysis. He also is responsible for discovering an important phenomenon called Oswald ripening. Oswald also didn't believe that atoms physically existed. And many other physicists also believe that physics should only be built on measurable, tangible, observable things. If it's too small to see, touch, and feel, it must be unscientific. Then came Einstein's theory on Brownian motion. He showed that the random jiggling of little particles in a sea of atoms could be used to prove that the sea of atoms really existed. And people made measurements of random jiggles of large pollen grains or grains of sand inside of a beaker of water before Einstein's time and saw the motion of their random jiggling and wiggling motion and said, whoa, these things are alive. Because if you couldn't see the atoms, you would think that this big black ball is just a living entity like bacteria or microorganisms. But Einstein said, no, those motions are from the bombardment of the sea of atoms that physically exist that transfer momentum onto the big ball that causes it to move. This thought was an absolute game changer. 3 years later, a French physicist, Jean Perron, made experimental measurements of Einstein's calculation and won the Nobel Prize in 1926 for these measurements. This completely settled the debate of whether atoms exist or don't exist. Today, I'll show you Einstein's calculation to measure the size of molecules, a molecular ruler, and also to measure Avogadro's number. Einstein had a quest to count molecules and calculate Avogadro's number as something we can measure and feel and touch, which together prove that atoms have a physical entity and that we can physically count them. 1, 2, 3, 4, all the way to 10 to the 23, Avogadro's number. Let's get started. Suppose that we have a Newtonian incompressible fluid. We know the constitutive relation for the stress tensor of this fluid, and it looks something like this. Sigma is the stress tensor at some point inside this fluid. P is the fluid pressure inside this fluid. Mu naught is the Newtonian viscosity of this fluid. And finally, we have a gradient of the velocity. Whenever there is fluid flow, it can create gradients, spatial gradients, in the way the fluid is flowing. This quantity right here is called the rate of strain tensor. And it is often denoted with the letter E, and because it's a second-order tensor, there are two lines underneath. Now, this equation, which is the Newtonian constitutive relation for the stress tensor, combined with Cauchy's momentum balance, gives us the famous Navier-Stokes equations. Just like that. Now, in Einstein's times, these equations were well known. So this is not the problem that he considered. The problem he considered was, into this Newtonian incompressible fluid, let's sprinkle a little bit of solute, some small little spheres inside this fluid. Just like that. So now we have a two-phase system containing both fluid, shown by these squiggles, plus these spheres that are sprinkled in dilute concentrations inside this fluid. Now, Einstein's goal was to figure out what is the analogous constitutive relation, or the stress tensor, of this suspension as a whole. We know already how the fluid should flow and behave inside the solvent, the Newtonian incompressible fluid part, but it wasn't so clear how the spheres should impact, for example, the effective viscosity of this solution. So our goal is to try to develop a stress tensor that looks like the following. Now, the brackets around the stress tensor, the pressure, and the rate of strain is an averaged quantity. We need to now deal with averages because we have both the particle and the surrounding solvent. So I'm going to define what the average is in a moment. But effectively, what we're trying to do is find an analogous equation like the one we have for a Newtonian incompressible fluid, except now we want it for this composite suspension containing both the sprinkled little solutes we've added plus the fluid. So here, bracket PF is the average fluid pressure inside the suspension, and mu effective is the effective viscosity of this composite solution. Imagine you take a beaker of water, sprinkle a little bit of solutes inside this water, and if you were to stir that solution, it's going to appear a little bit more viscous. It's going to be a little bit harder for you to stir this beaker because now you have particles inside your fluid, and that's going to create a larger viscosity. So our goal is to figure out what this effective viscosity is by trying to work on this system to put it into a form that looks like the one shown in pink. So let's get started. First, I like to discuss what the brackets mean. Let's define what the average is. The bracket average is an integral of the quantity over some control volume and integrated over the volume V. Let's define our control volume. So now this V is a control volume, like I've shown you here. And this volume, as you can see, contains both particle volume and the fluid volume. First, the particle volume. You can see, obviously, that this control volume contains particles inside them, and therefore, a part of this volume contains particle volume, Vp, and the rest of the constituent space inside this volume is the fluid volume, given by Vf. Good. So now the interpretation of the average is a bit more clear. It is, I have a stress tensor inside this fluid that is well defined in every point inside this volume. I'm going to add up all of those stresses, both inside the particle and outside the particle, add them all together, and divide it by the whole control volume. And that is the average stress inside this volume V. I can analogously define the average of the rate of strain tensor, and that should just look like the following. Just like that. Now, I'm going to do a quick calculus on this term right here. This integral is a sum over two volumes, which from basic calculus we know that we can split this integral into a sum of two separate integrals. Let's write that down. All right, I've written in a little bit of a spooky fashion, but let me just describe what's happened. First, I took this integral, added two separate integrals, one over the fluid volume, Vf, and one over the particle volume. That's totally allowable by calculus, right? Just split an integral into two. Now, first, the stress tensor inside the fluid volume is just the Newtonian stress tensor. Right? You've already agreed that if I just have the fluid, everywhere inside the fluid space, we just have a well-known Newtonian stress tensor. And this existed by Einstein's time. So I'm just written down here the Newtonian stress tensor. Literally, sigma is equal to this term inside the parenthesis. That just came straight down. And we could do this because we are integrating over the fluid volume. We know exactly what the stress tensor is inside this fluid. Now, over here is just the rest. This is the stress tensor that came straight down, integrated over the particle volume. This term we can't really do much about yet because we don't know what this stress tensor inside this rigid solid body looks like. So, one more little trick. I'm going to add and subtract a term. All I've done here is to add this term, 1 over v, integral of the particle volume, 2 times the solvent viscosity, eta naught, rate of strain, dv, and subtracted the exact same term. So this term and this term are identical. I've just effectively added 0 to the quantity. Add and subtract the same amount. They cancel, but I've written it this way because we can start to now massage this equation and put it into a form that looks something more like what we want at the very end. First, we can combine these two terms together like the following. All right, so I've combined this term from the first integral from the term that we just added into a single integral where I've just combined the volumes of the fluid and the particle. I've put the 2 times mu naught outside because those are constants that just come straight out of the integral. Now, if you look at everything here, this is the definition of the average rate of strain inside this control volume. So we have 2 mu naught times the average rate of strain. This term over here is the pressure integrated over the fluid domain. That's just the definition of the average fluid inside this control volume. Just like that. Again, using the definition of the average, but this time we're averaging over the fluid volume. So this term right here inside the integral plus the second term we added is completely done. All we need to do is to figure out this last integral over here. First, we're trying to figure out the integral inside the particle volume. So that's the region that I've shaded in pink over here. First, the rate of strain inside a solid rigid object is 0 because there's no flow happening inside of a solid rigid object, right? Rate of strain E is a velocity gradient. Things have to be flowing and moving. That could definitely happen inside the surrounding fluid, but if we're inside the particle, for a rigid solid object, there are no fluid flows happening inside. Therefore, the rate of strain, or the flow inside the particle, must be 0. So that term completely goes away. So all we have left is an integral of the stress tensor inside the particle volume. This is a little bit tricky, so let's consider one thing. The one thing I want to consider is a small little aside on tensor and vector calculus. What is the divergence of a dyadic product of the stress tensor sigma dyad product with the position vector x? Let's first define what the position vector is. The position vector x is some vector from a lab fixed frame that points to a point inside of the system. So once again, what is this quantity? Well, if you've seen my lecture on Einstein index notation and the notation that Einstein developed as part of his general relativity, but also his fluid mechanics, is to be able to do these types of higher tensor calculus and derivatives. So if you know how to use Einstein index notation, this is no big deal. First, we just translate this vector and tensor form into Einstein index notation, and we just take the derivative. In this case, the product rule. Just like that. Partial xk, partial xi is just the Kronecker delta function. Delta ik. So now the rule is that delta ik will swap that I to a k. And therefore, we can come back to our original question, and in vector and tensor form, this would look like the following. Just like that. Now, let's go back to the Cauchy's momentum balance. The problem that Einstein considered was a situation where we have small little microscopic solutes or particles sprinkled inside of the fluid. Therefore, we have a low Reynolds number situation where inertia is not important. So the left-hand side is 0. He also considered the case where the spheres are neutrally buoyant and there are no external forces acting on the body. Gravity doesn't play a role because they're neutrally buoyant with the background solvent. And therefore, there are no external forces inside the fluid. So all we have, apparently, is that the Cauchy's momentum balance, which is a fundamental law of physics, momentum is conserved, tells us that the divergence of the stress tensor is equal to 0. Therefore, this whole term goes to 0, and all we have left is that the stress tensor, apparently, is equal to the divergence of the dyadic product of the stress tensor times the position vector. So we could just use it right here. We can replace this stress tensor with the divergence on the left-hand side. I just realized that I forgot a 1 over volume over this integral on the right-hand side. I think you probably got that, but right now I'm going to add it. Just like that, to add it to the whole term. I think you're able to follow along. So what I'm going to do now is to take the divergence theorem of this quantity right here. We can integrate over the volume or just place it onto a surface. That's the divergence theorem. So now we have a surface integral. That's what that little hoop indicates, a surface integral over the particle surface. So we're no longer going inside the volume of the particle. We're now on the surface. We're trying to take this integral along the surface area of the particles inside of our control volume. Now, if we have indistinguishable particles that are all identical to each other, then this integral right here should just be the sum of each particle surface inside this volume. So what we can do is to, instead of taking the integral over the total particle surface inside this control volume, we could just do it over a single particle surface and multiply it by the number of particles inside that volume. Just like that. So all I've done is to change the bounds of the integral to be not over every particle surface, but just over a single sphere, for example, this one, but multiply by n of them because there are n particles inside of our volume. So if the particles are identical, indistinguishable, you can make this swap. Now, everything inside of here is called the hydrodynamic stresslet. Just like that, the hydrodynamic stresslet. So this is where we actually have to do some fluid mechanics, which is what Einstein was doing during his thesis. As a PhD student, he was working through these integrals. So let's consider what the hydrodynamic stresslet is for the particular problem that Einstein worked out. The idea behind calculating the hydrodynamic stresslet is to suppose that we have a single particle, and we're going to subject this particle to some kind of test flow. We're going to subject it to a test flow and see how that particle disrupts the fluid and the stress in the surrounding solvent. Now, it turns out any general linear flow ends up working out, but the flow that is very convenient, and the one that Einstein considered, what's called uniaxial extensional flow. It looks like this. In uniaxial extensional flow, we have velocity streaming in through the sides of the particle, and because volume of fluid must be conserved, that fluid has to go somewhere, and it gets squeezed out, up and below. This is called uniaxial extensional flow. So if you have this type of flow subjected to a rigid particle of radius a, you can actually work out the fluid mechanics of what does the surrounding velocity field look like when you subject this particle to this flow. Now, it turns out this is a lot of algebra. I remember being a graduate student working this out using full Einstein index notation, rolling up my sleeves, large sheet of paper, large table, lots of erasers flying everywhere. I'm going to skip that here and just write down the final result, but one can actually solve this. All you have to do is solve the Stokes equations, this Cauchy's momentum balance with the Newtonian stress tensor, subjected to a uniaxial extensional flow happening very far away, and you can calculate the velocity disturbance that this particle generates on its nearby fluid. It looks like the following. Just like that. This comes directly from solving the Stokes equations, plugging it into here, and just evaluating the integral. Out comes this numerical solution. Again, A is the particle radius, mu naught is the viscosity of the solvent, and this is the average rate of strain that you've imposed from far away. Now, physically, what does a stresslet correspond to? If you were to have a fluid flow that comes in, hits one point, and streams out above and below, then the fluid wants to stretch along the extensional axis of shear and compress along the compressional axis of shear. But the existence of the particle, a rigid particle, resists that. Because this is a solid object, it cannot stretch into a shape of a football. Ideally, from the perspective of the fluid, it wants this particle to start streaming up in the shape of a football and get narrower on the compressional axis and stretch longer and longer along the extensional axis. That's what the fluid would like it to do. But because this is a rigid object, it resists that. It's saying, nope, I'm not going to stretch. And that resistance of stretching is exactly manifested in the form of a force or a stress that the particle generates on the surrounding fluid. And it's given by this quantity right here. Now, Einstein was very clever in choosing this test flow because if you were to put on uniform flow or rotational flow, you're going to generate a net force and torque on this object with Uni-exoextensional flow, there's no force, there's no torque on this particle. It's just neutrally buoyant, hanging out there. It's just resisting elongation and stretching. So out comes this form that we can plug into this hydrodynamic stresslet to make more progress. We're almost there. Let's plug this into here and clean up a little bit. We get a form that looks like this. All I've done is to take this expression, put it into here, combine it with this integral up here. So first we have the n that drops straight through. I've split up the 20 into a 4 times 5. Everything else just comes straight through. Pi a cubed divided by 3, pi a cubed divided by 3, mu naught, rate of strain, average. Now we have the 1 over volume that comes straight down, and the number of particles, n. The reason I wrote it this way is because everything here is the definition of the volume fraction, which I'll denote as phi. The volume fraction is what fraction of my control volume is occupied by a solid object. So it's Vp divided by the total volume V. And you can clearly see that. Vp, the volume of particle inside this control volume, is simply the volume of each sphere, which is 4 pi a cubed divided by 3. That's the volume of each sphere. And there's n of them inside my volume. And therefore, this is the total occupied volume by particle divided by the total volume of the control. Therefore, this is just the volume fraction. OK. We are there. Let's now combine the average fluid pressure, the average rate of strain, with this new contribution from the particle to write our final expression for the average stress tensor. You get something that looks like this. Average stress tensor is equal to average fluid pressure plus the rate of strain component coming from the fluid volume plus this correction that Einstein calculated, which is 5 times the viscosity of the solvent times the volume fraction of the solute that you added times the rate of strain. Now, these two terms can be combined into one term. And it looks something like this. All I've done is to combine these two terms together. So we have 2 mu naught, 1 plus 5 halves phi, bracket, whole thing, times the average rate of strain. Now we're done, because you can now see what Einstein just did. He took this original form that we were trying to get towards, which is the average stress tensor, and our goal was to figure out what the effective viscosity of the fluid suspension was. So now we can clearly see that if you just compare like terms, so the right-hand side, we have negative of the average fluid pressure times the identity tensor, plus 2 times some quantity right here. That quantity is our effective viscosity times the average rate of strain. So let me just write down the final result that Einstein calculated as a part of his thesis. Here it is. This is the effective viscosity of the suspension. Earlier I said if you sprinkle up solute particles inside of a beaker and stir it around, what is the resistance you'd feel? Here it is. And of course you would expect it to depend on how much solute you sprinkled into the beaker. That's phi, the volume fraction. That's the concentration of the solute that you put inside. And of course, you have this 1, which is the original viscosity of the solvent, plus a contribution due to the fact that you've put in the solute. And as you stir it, it's going to disrupt the fluid flow around it, and therefore it's going to cause the viscosity to increase. It is a profound calculation that he did. This correction right here, 5/2 phi, is called the Einstein shear viscosity correction. And he published this in 1906. He did the work in his thesis in 1905 during the miracle year, and it takes some time for it to get published. But here was the original calculation that he did that ultimately came out in 1906. Now that we derived this very important result that Einstein, 26-year-old Einstein did during a part of his thesis, I wanted to come back to the main result. By the way, most students don't know that Einstein was doing fluid mechanics. And he invented his notation of the Einstein index notation, which later became really useful for general relativity and also for his calculations here. But again, he was after a bigger question. He wasn't just doing fluid mechanics for the fun of fluid mechanics. He was trying to prove the existence of the atom. So you might wonder, how is this even related to the existence of the atom? Well, let me just combine this equation with a little bit more clarity and combine it with another equation that will get at the core of where it relates to Avogadro's number. All right, here is Einstein's shear viscosity correction expression, which actually ends up being accurate to about 10% volume fraction. If you sprinkle in a little bit of solute particles inside of a Newtonian incompressible solvent, take it on a rheometer and measure the effective viscosity, this is pretty good to about 10% volume fraction. Again, this is a theory that was developed for dilute, non-interacting spheres inside of a system. And it's pretty good. But once again, Einstein was onto catching bigger fish. Fluid mechanics was just a drive-by on his way to calculating Avogadro's number and proving the existence of the atom. So let's think a little bit more about the right-hand side. Here I've just rewritten the volume fraction from its original definition. Now, the number of solute particles, n, the number of solute molecules inside the system is the mass that you've added, how much sugar or how much solute that you can weigh on a balance, how much you've added, divided by the molecular weight. So let's just check the units on this real quick. So mass divided by the molecular weight is kilograms divided by kilograms per mole, right? Molecular weight is kilograms per mole. And therefore the kilograms cancel, and we have mole upstairs, and Avogadro's number is the number of particles per mole. And therefore, the moles cancel, and we indeed have the number of particles, n. So that makes sense, right? So we can replace n with mass divided by molecular weight, which are things that one could measure, and it was known at the time. We knew how to measure things in Einstein's time in 1905. We knew the molecular weight of many chemicals and molecules, and n sub a is Avogadro's number, which was unknown at the time. Again, these things were debated. So we've successfully inserted Avogadro's number, which was Einstein's quest to begin with, into this expression of the shear viscosity correction. So here we have it. We have this expression where we've put in the Avogadro's number, which is an unknown, into this expression. we can measure the mass by just weighing it. Chemists knew how to measure and determine molecular weights. And finally, V is just the volume of water, or the total volume of your system, which is easy to measure. So, mass we know, molecular weight we know, volume we know, the size of the solute not known. So A and Avogadro's number were not known. Again, I introduced this lecture as a molecular ruler or a solute particle ruler. And so A was not known. On the left-hand side, the viscosity, there were rheometers already available at the time. Actually, many types of rheometers. In fact, there were some that I just wrote down here. Capillary viscometer, one was called the Oswald viscometer by Wilhelm Oswald, the atom non-believer. So it's ironic that this instrument was used to prove the existence of the atom. A falling ball viscometer, you just drop a ball, measure the velocity at which it's falling. By relating the mass of the ball, the velocity, the gravity, you can measure the effective viscosity of a suspension. So, left-hand side, completely known, and there were data available by Einstein's times. Over here, the unknowns are the size of the solute, or the particles, A, and Avogadro's number. So, we have two unknowns and only one equation. So clearly, Einstein had to come up with another expression, and that is his extremely famous paper from 1905 on Brownian motion. In 1905, Einstein derived a relationship between the diffusivity of a solute inside of a fluid and the thermal energy of the bath. It looks like this. The diffusion coefficient D is equal to the thermal energy, Kb, which is Boltzmann's constant, times the temperature of the system, divided by the denominator, which is the Stokes drag factor. So Stokes played an important role in this theory. Stokes solved for the drag coefficient, which is 6 pi viscosity of the solvent, mu naught, times the size of the object suspended inside the fluid, A. So a lot of times, this relationship is called the Stokes-Einstein relationship. Now, we can rewrite the numerator, Boltzmann's constant, and insert Avogadro's number into it. And the way we relate Boltzmann's constant to Avogadro's number is simply the gas constant R divided by Avogadro's number. And by the mid-1800s, the ideal gas law was well established, so the gas constant R was a well-known value. So we're now able to insert the unknowns, A, which comes from the Stokes drag equation, and Avogadro's number, N sub A. So we have two equations with two unknowns. And by the way, this expression is called the Stokes-Einstein relationship, but there's a small little piece of important history that I wanted to mention. In addition to Einstein in 1905, there was another scientist who derived the exact same identical relationship between the thermal energy and the diffusion coefficient. There was a Scottish-Australian physicist, William Sutherland, who was independently working on the same calculation. And a year before Einstein submitted his paper in 1905, in 1904, he actually published this paper in a journal in Australia. And it just didn't get the same kind of attention that many of the communities in Europe were getting, because Europe was very much the hub of science and physics back in the early 1900s. And there wasn't a lot of exchange between a scientist based in Melbourne, Australia, and a bunch of giant famous names over in Europe. So unfortunately, Sutherland's very important derivation of the same result that Einstein derived didn't get a lot of attention, and the rest was kind of history. He was left out from this very important expression. So actually, there are a lot of people that now call this expression the Stokes-Einstein-Sutherland relationship. I happen to be one of them. So if you look at my papers, we'll write down this expression and say, this is the Stokes-Einstein-Sutherland diffusion coefficient. So just wanted to give William Sutherland important credit for a very important result that I think he deserved, especially because he arrived at this result independently and published it a year before Einstein. So now Einstein came up with this argument of the osmotic pressure of the water molecules bombarding into a big particle balanced by the drag force felt by the particle. That's what this balance is. It's the thermal energy of the atoms, if they exist, around the big particle bombarding into it, and that will exchange a momentum on the big ball, and as it moves, it's going to be dissipated by the drag of the surrounding solvent. So it's a balance of the pressures that the atoms generate on a big particle that then dampens due to the viscosity of the background solvent. That's what this expression is saying. And it is manifesting in a term, a diffusion coefficient that is measurable. We can actually observe the jiggling around motion of pollen grains, of sand grains inside of a microscope. So we can see these things wiggle around, and that must be due to the bombardment of the atoms. That was the train of thought that he came across. So now we have this equation over here with two unknowns, this expression right here with also two unknowns, A and Avogadro's number. We have two equations, two unknowns. And by the way, the diffusion coefficient, like the viscosity, measurements existed. So data on the diffusivity also existed. The diffusivity of salts, sugars, small little particles inside of water existed. People had diffusion columns from Fick's times, Fick of Fick's first and second laws, Fick's constitutive relation, back from the mid-1800s. So people can measure, for example, you have some water or some solvent in contact with another type of solvent containing small little salt, sugar, small particles, and you can look at the spread of that interface as it meets and how that spreads out in space. And by making measurements of that spread, people had data on the diffusion coefficient of these species. There were also optical and inference methods where you can shine light at an interface and watch that interface spread out and how it refracts light through the mixing of the interface. And that usually resulted in pretty accurate data on the diffusion coefficients. So Einstein, back in 1905, 1906, around that era, there were very good measurements of diffusion coefficients, of viscosities, of sugar molecules like glucose. So he took data on sugar molecules, diffusion coefficient, viscosity, mass, molecular weight, which was known by chemists, volume, and had two equations, two unknowns. And he solved these equations using available data on glucose and came up with the following numbers. size of the solute molecules. Glucose, 4.9 angstroms. Avogadro's number, 6.5 times 10 to the 23. Remarkable. Absolutely remarkable. This is such a good result from thought experiments he's having, showing that atoms bombard into a sphere that we can then measure through its motion, and how it might change the viscosity of a fluid that's stirred. We can calculate to the right order of magnitude the right result of 10 to the 23, 6.5 times 10 to the 23. Never mind that he had a typo in his thesis that a very diligent reader caught him. So he initially missed this 5/2 factor. Never mind that. And never mind the other data that he used that was actually improved a little bit later on that resulted in this better number. So there were a couple of iterations that he went through. But at the end of those corrections, he got these numbers, which I find absolutely insane and remarkable how good his ability to think creatively about how to count atoms, and locate a ruler for sizes of small solutes and molecules. It's absolutely insane. Okay, I just wanted to finish with now an experimental validation of Einstein's relationship of the diffusion coefficient and counting Avogadro's number. After Einstein proposed his theories on Brownian motion, a couple years later, a French physicist, Jean Perron, experimentally validated his theories. What he did was a painstaking experiment where he was looking under a very, very good microscope at the time, and actually, by hand, tracked the mean square displacements of the small little grains that he put inside of a solvent. By hand. This is a page out of his notebook where he's actually taking line traces of where the object resided in as a function of position, and each of these streaks tell you a time trajectory of where that object went. So this is a direct confirmation of Einstein's theories that molecular bombardment of atoms on the big spheres can result in its net displacements. When you calculate the position of the objects correlated with itself, this is called the mean square displacement. This is like the variance of the spread of this object in space. Plot it as a function of time. Its slope at long times gives you the diffusion coefficient of the object. This is what Einstein predicted, that you can actually keep track of these particles as they're jiggling around and measure its displacement over longer times through a diffusion coefficient. And furthermore, that diffusion coefficient is related to the thermal energy, kT, divided by the drag through the Stokes-Einstein-Sutherland relationship. So this painstakingly meticulous experiment by Jean Perron won him the Nobel Prize later in 1926 for playing a key role in proving the existence of the atom. And actually, if you look into his notebook, there's a page that looks something like this. So this is Jean Perron's notebook. Really cool to see notebooks of these famous scientists. And you can see he's doing these traces. It's really cool to see. You can see the individual traces. I think the numbers next to the vertex are time points, maybe? And he has some scribbles around there and some lab notebook. Really cool to see. In any case, this concludes the history of how the existence of the atom came to be. It came from a really creative scientist, Albert Einstein, who said that the thermal motion of small little atoms can collectively synergistically bombard into a larger solute molecule, and we can actually further see their motion over long times. And if we can see their motion, that means that we can count the atoms that were inside. We can touch them, feel them, smell them, see them. There are things that are now tactile objects that can see, observed, measured, touch, count. And that was Einstein's quest for Avogadro's number and how he proved the existence of atoms. And by the way, that was one of his papers from 1905. 11 days later, he was thinking about special relativity, on the side. So his work on fluid mechanics was a very important part in how it impacts all of our lives in the existence of the atom. Now, I think Einstein's quote resonates with a lot of us. Life is like riding a bicycle. To keep your balance, you must keep moving. Good luck to everyone with all of your research, all of your endeavors. We can use a lot of life lessons from this very famous quote that I love from Einstein. Let's keep our balance. Let's keep moving. See you next time.